Okay. So it's time to begin the second day's set of talks. And the first talk will be again by Professor Guruprasad of ISI, Kolkata, and he's going to tell us more about quantum information.
So, no. I forgot to bring the mobile. Good morning to all of you. So, yesterday we saw the postulates of quantum mechanics. Only thing that I have to tell the postulates regarding composite system. And composite system is described. So every system has to be associated with a Hilbert space. So if you take a composite system like bipartite or tripartite or n-partite systems, then what is the Hilbert space that is associated with the system? You have to specify. So if you consider true quantum system AB, and this is associated with a Hilbert space HA, this is Hilbert space HB, then the composite system has to be described as HB. But some people think that it should come out as a theorem that if single system is associated with Hilbert space HA, then composite system must be described by HB, but still some people like Christopher Fuchs was trying to prove this thing, but still it is a part of the postulate. So after this thing, that you associate this thing in this way, and there are other things that remains there, like we described. Only thing that Hilbert space that is associated with the composite system AB is associated with the Hilbert space HA tensor HB. So you have to be careful only when you are taking a operator acting on some psi tensor phi, where this belongs to HA, this belongs to HB, then you have to be careful that operator acting on the Hilbert space should act on vector in that Hilbert space. You don't write like B acting on psi and A acting on phi. So this is defined in the Hilbert space HA, this is defined in the Hilbert space HB. So you should act them accordingly, and it will be A acting on psi A, tensor B acting on phi B, like that. And also, when you take a scalar product between, say, psi A tensor phi A, and say chi A tensor gamma, sorry, this is B, gamma B, then you take the scalar product in the same Hilbert space. Don't confuse with some vector from this Hilbert space and some vector in this Hilbert space. So you have to take care of this thing. But before proceeding, let me tell you one thing that so if
excuse me, why the different notation? I mean, you have psi A, psi B, then the second line you have then you have psi alpha, gamma beta.
Oh, this is a vector. This is a vector. I am telling you, if you take a scalar product between them, you take a scalar product within the same Hilbert space.
Scalar product
Between two vector, you keep confined in the. And one more thing I have to tell, that if you consider a operator A, then you know what is trace of A. Trace of A means generally sum of the diagonal elements, but A can be expressed in so many ways, where it is diagonal, where sometimes it may not be diagonal. So general formula is something like this. We choose the orthonormal basis I, complete orthonormal basis, then trace is nothing but and And this is actually invariant under change of.
A is both the Hilbert space, the subspace of Hilbert space.
No,
and
no, no.
operator.
A is operator acting on some Hilbert space.
A is an operator.
A is an operator. So I am defining trace of A. Trace of A, you consider any orthonormal basis.
Oh, because you also use it as a substrate for the Hilbert space itself.
No,
You
H.
use A. You use A.
Oh,
Both
yeah, you are correct. Sometimes I am referring A for a system, sometimes. So maybe, yeah. Yeah, sometimes here I am using A as an operator acting on this system. So maybe I should write operator O.
also A.
O acting on some Hilbert space. O is an operator.
Sub A.
Yeah.
Sub A.
Yeah, but now I am considered as a single system. So you choose any orthonormal basis. So you may be thinking if I choose some other orthonormal basis, then test may change. It does not. And that is a homework also. If you take another orthonormal basis, trace will remain same.
I have a question that's maybe beyond the scope of whatever I want to talk about it later. If you have a fermionic system, you have fermions, identical fermions, and A is one subspace, B is another subspace, then the Hilbert space will not factorize.
Yeah, maybe you have to put some super selection rule, keeping in mind these statistics. Yeah. So when I'm telling that every unit vector is a state, then if it is not, then I have to put some super selection, telling that nature does not allow some of them.
So you are assuming that A and B are made up of distinguishable entities.
Yes.
Can we write them as tensor product of Hilbert space because they have simultaneous? Because they can find
Again, it is part of axiom. I am not going. I am not.
So the answer was that any operator in A, any operator in B.
Yeah. But I am not trying to justify why tensor product is the proper way of representing the system, because that is a part of a research. Now, let I consider these are all these things I am trying to do to make our life simple. This is an operator already. So can you tell me the trace of this thing? Because you think about it, that trace is invariant under change of basis. I mean, you can take any orthonormal basis. So keeping that in mind, can you tell me what is the, so trace is a number. No, what will be the number? Yeah, scalar product. Because you choose the orthonormal basis in such a way that psi is the first element. Then actually only term that will survive is makes our life simple. And not only that, if you take trace, maybe A into psi and phi, then also you can make your life simple. Now you take phi, orthogonal basis, so that phi is the first element. Then only that term that will survive, phi, A, psi. Only this term will survive. So actually, you see that operator can be written as so to write this thing and take trace, life will be very simple because trace is linear also. Now I consider two spin-off particle. I consider the simplest basis, sometimes called canonical basis, which is eigenstate of sigma z. Let I consider two system A and B associated with a two-dimensional Hilbert space. I am restricting myself to two-dimensional Hilbert space, complex Hilbert space. And this is the orthogonal set. Now, if I write a state like this, this means my first particle, or I write 1, 2. And if I write some operator A, then I will not confuse. I consider two systems, 1 and 2. Then what this description tell? State of the particle, first particle is 0. State of the second particle is also 0. I consider another state like this. Again, this one refers to system, and this one refers to something confused. And this one refers to ket A, means down eigenstate of sigma z. Now, this tells similarly that state of the particle 1 is 0, state of the particle 2 is ket 1. But I can combine them because they are also orthogonal. So AB, where AB non-zero, then can you tell me what is the state of the first particle and what is the state of the second particle? First particle is 0. And second particle? This is the state of the second particle. So I can specify what is the state of the first particle, what is the state of the second particle. Very good. Now I consider these states. Now tell me the state of the first particle. Yes? What is the state of the first particle? Yeah. So particle has no state. No, you tell in terms of vector, but it's not coming, no? But globally, it is a unit vector. Globally is a perfect vector in the tensor product Hilbert space. So globally, the state is defined. When I am asking you the state of the subsystem, you cannot tell immediately. That's why it is entangled. Entanglement means that global system has a definite state. Pure entangled, till now I am confining myself to pure entangled state. Pure entangled state means global state has a definite. Global state can be defined by a definite vector, unit vector. But local system cannot be represented as a unit vector in that particular Hilbert space. That's entangled. Now some of you know that actually the state will be mixed state. So this is very nice. Globally, it is perfectly in a definite state. Locally, it is not in a definite state. It is a mixed state. So how to find the, now there is a prescription, how to find the subsystem state of the subsystem. The general prescription is rho AB your state of the density matrix of the joint system, then what you do, you take partial trace over B. I mean, you take only trace over B part. If you consider an operator acting on this tensor product Hilbert space, but if you take partial trace over one of the Hilbert space, then finally what you get? Trace generally gives you a number, but if you take partial trace, earlier it was acting on the both of the Hilbert space. After partial trace, you will get an operator acting on one of the Hilbert space. And in this way, to get the state of the particle A, you have to trace over B, and if you are interested in the state of B, then you have to take trace over A. And for this state, you have to write it in terms of density matrix. Now, if you are interested in the state of particle A, you have to trace over B on this density matrix, and finally you get mod A square 0, 0 plus mod B square 1, 1. So it is a mixed state. And similarly, rho B will come out same.
This sign is square, yes? I mean,
Yeah, 2. So this is the idea. Now, we are coming to a, so I have written this state in a very nice form. This 0 is orthogonal to this 1, this 0 is orthogonal to this 1. So sometimes life may not be that simple. It may be non-orthogonal states. So life may not be that simple. But speed decomposition tells us that if you consider a pure state for bipartite system, I mean, if you take two systems and consider a pure state, always it can be written in this form. Maybe the basis may be different. So what I do.
Sorry, just a mental quotation. The last time, right, rho A is equal to weight for the subscript AB should be both for the
So, yeah, so this will be A, this will be A.
The trace of the wrote psi AB psi to be psi AB, AB psi. The AB is both of the head.
So I have replaced them by a single, because again I have to write ABA. Now life has been made simple by speed decomposition theorem. So if you take a orthonormal basis for system A or system 1, and now I write system A because I am more associated with telling system A, system B, because Alice Bob is coming in the picture. And some K, B system, B. Another orthonormal basis for B system, then any joint state which is pure can be written as because I tensors because this is an orthonormal basis, this is an orthonormal basis. If you take a scalar tensor product of them, then there will be orthonormal basis for the tensor product Hilbert space. But the number will be number of the member of this orthonormal basis. It is dimension of A into dimension of B. So any vector, any unit vector can be written in this form. But so how many terms are there in general? If both system are d squared terms are there in general. But the bases have been chosen by yourself. But there is a nice choice of bases such that you can write this same state as di some psi I. Insert. This is for A. You can write them in terms of only d number of terms. And not only that, this is orthogonal basis. This is also form orthogonal basis. But if you choose the basis, so next question is how to choose that basis so that it can be written in this nice form. The prescription is something like this. You calculate rho b. How to calculate rho b? Case of psi AB and trace over A. So you get a density matrix rho b. After getting the density matrix rho b has a spectral representation. Because rho b is a positive operator, all eigenvalues are positive, and that is say phi I. Then, and also you can find rho A, and you can check for every pure entangled state the eigenvalues of the reduced density matrix will be same. It will be some so a state can be written as so what is the prescription? Prescription, if you are given a general pure state in a bad form, having d square or d square minus 1 or d square minus 2 terms, you want a nice form. What you do, you calculate your state reduced density matrix, find the eigenvalues, find the eigenvectors. Similarly for rho A, find the eigenvalues, eigenvectors. I am telling you, eigenvalues will be same. Eigenvectors will form an orthogonal basis. Then you prescription is it can be written in this form. It can be proved by using polar decomposition theorem. Polar decomposition theorem tells that polar decomposition theorem tells that any operator can be written as some u d v, where d is a diagonal matrix with positive entries and uv are unitary operators. Using that theorem, it can be proved, and in Nielsen-Chuang, you will find a nice proof. But I am not going in the proof. I am only claiming that every pure entangled state admits this kind of simple representation, where these psi i's are orthogonal with each other, phi i's are also orthogonal with each other. So it has a very nice form. And if you have this form, then calculating the reduced density matrix becomes very trivial. What will be the reduced density matrix of particle A? It will be nothing but sum of di square psi I, because you are tracing over B part. So it's become very simple. Now, last time I was telling you that if you have a mixed state, it can have infinitely many possible representation. That means it can be prepared in infinitely many ways. Already I wrote one, that identity by two can be written in this form. But identity by two also can be written. So identity by two, this is the density matrix for a qubit. This can be written as half 0, 0, plus half 1, 1. This same thing can be written as half plus half minus minus. Again, that 1, 1/4. Yes, the beauty is phi can be anything. Some A0, most generally A0 plus B1, only normalized. And sigma 0 is equal to identity. Sigma 1 is sigma x, sigma 2 is sigma y, sigma 3 is sigma z. And I actually told you to derive this relation. Not only that, there may be some other representation where from chi I, where I is equal to 1 to 50. So it may have many decomposition, and number of terms appearing in the decomposition may be anything. But AJW theorem, Huxton, Jossa, and Luther's theorem, discovered in the same year, the teleportation protocol of Bennett and Bashad and other people were discovered. This tells that if you don't put any restriction on the dimension of this system, then you can prepare a psi AB such that if rho B is equal to, so rho B is the density matrix of B, and I am telling you rho B can be prepared in so many ways. It has so many representations. But for a given rho AB, always you can perform some measurement on this system so that you prepare the particular representation someone wants. It has infinitely many representations. Yeah. Yeah. No, mixed state does not admit any composition. I don't know how to answer your question, but it is very simple. That mixed state is mixture of pure state, so those pure state can have Schmidt decomposition. That is the theorem. So you cannot ask a question. Maybe. No. Yeah, you can find Schmidt number of a mixed state.
Use the microphone and asking questions so that it gets recorded.
So I think we can find the Schmidt decomposition, but the problem is like here the vectors are in the Hilbert space, but when you do operator Schmidt decomposition of density matrices, like you'll get operators that we don't want, like we won't want we won't get actual observables in those decompositions.
I don't think the theorem can be extended in this way in operator space, because operator space, this scalar product and all these things has to be well defined. But what is true is that you can define a Schmidt number for mixed state, and it has to depend some minimum over something like that. But the Schmidt decomposition is not allowed for mixed state. And I don't know how to define even a Schmidt decomposition. Yeah, but what I am trying to tell is rho B is the reduced density matrix, then rho B has infinitely many representations, then there exists a pure state psi AB, for which I have calculated this rho B. It has infinitely many representations, but by performing measurement on this particle, you can prepare whatever representation someone wants. This is very beautiful. Let me tell you one example. Yeah. I consider this a state.
Hello. Yeah, so what you mentioned is that there is a pure state. There is a pure state, rho b, that you have written down.
No, rho b is not a pure state. Rho b is a mixed state. If I take a pure entangled state, then rho b must be a mixed state.
Okay, so you said
but
that
rho b can be prepared in infinitely many ways.
yes, but all the physical quantities that you're going to measure have nothing to do with the way you decompose rho b, right?
That's why that's the thing I am going to tell. It has no physical meaning. Now, when I write in this form, there is in between, there is a tensor symbol, but I am avoiding. This is for A, this is for B. So this is a maximally entangled state because it would trace out. This why this is called maximally entangled state. There are so many support, like it violates Bell's inequality maximally. It gives you teleportation, it gives you dense coding, which I am going to discuss. So people call it maximally entangled state. And not only that, if you calculate the entropy of the, which you are more interested in, this von Neumann entropy of the local thing, this one. But this same state can also be written, this is very peculiar property, plus the same state can also be written in the eigenbasis of sigma x, written in the same form. Now, rho b, already I wrote rho. So identity by 2 can be prepared by taking equal mixture of 0, 1, but at the same time, identity by 2 can be prepared also by taking equal mixture of plus and minus. Now, let this state is shared between A and B, and B tells you prepare these ensembles. If B tells that you prepare me these ensembles, A will perform the measurements in the 0, 1 basis, sigma 8. With half probability, this particle will collapse on 0. With half probability, this particle will collapse on 1. So density matrix will be, again, identity by 2, but the representation will be equal mixture of 0 and 1. But if, say, this side is Bob tells, no, you prepare me these ensembles. These ensembles. Then Alice again can prepare it. Alice will measure in the plus minus basis. Again, with half probability, Bob's thing will be plus and half probability, Bob's thing will be minus. At least in 2 cases, we saw that whichever ensemble other people wants, it can be done. Now you see, if these 2 can be distinguished, yesterday we were discussing these 2 cannot be distinguished. It could be distinguished. Then B, if they could be distinguished, I mean, these 2 representation could be distinguished, then B can tell which particular measurement has been performed by Alice. And in principle, they can be light years away. So B can tell which measurement has been performed by A. So in this way, you can send real information from one place to other place instantaneously, even if they are light years away. So that's why last day I was telling these 2 boxes. One box is containing both the box containing large number of particles. One box was containing 0 and 1, and the other box was containing plus and minus. I was telling whether the box can be distinguished. If it could be distinguished, then actually by using this thing, you can send signal instantaneously. Anyway, but here it has only two components. It has only two components. 0, 1, plus, minus. But here, how many terms are there? 4. How do you prepare this thing? Because Huxton-Joshua-Utter's theorem tells that whatever, even if this rho B has 50 terms, that also can be produced by performing some measurement on particle A. This is miraculous. But let us tell how this, with 4 terms, how this can be prepared. And it is nothing but earlier stage of teleportation. See how to do it. You take this state, you take another, because I am taking whether by performing some measurement in this lab, you can prepare the particular representation. These or these. These two already we have checked. Now we are checking these ones. How to prepare this one. You take a particle which is in a state psi. You perform a Bell measurement. What is a Bell measurement? Bell measurement means I'm writing orthogonal basis in tensor product Hilbert space. Now I am again making things simpler. 0, 0 means first refers for A system, second refers for B system. Similarly, first refers for A system, second refers for B system. This is only minus. This is orthogonal basis. And most of you belongs to condensed matter physics. So actually, how to prepare this kind of a state, at least first one. So you start with 0, 0, put a Hadamard on the first particle. Hadamard, how it acts? It takes 0 to 0 plus 1 by √2 and 1 to 0 minus 1 by √2. And there is another gate too. It takes 0, 0. First is source, second is target. If first is 0, it does not change. If first is 1, it leaves the second. Using this kind of gate, I mean, both are 0, 0. Put a Hadamard here, then put a C0 here. Finally, you get 5 plus. And challenge is really create Hadamard transformation and C0. Then you can create entanglement.
Sorry, I didn't get the C0. What is the C0?
C0, oh, I full. C0 is C0 acting on 0, 0 gives you 0, 0, 0, 1, gives you 0, 1, 1, 0, gives you 1, 1, and 1, 1 gives you 1, 0. That means it changes the state of the second qubit if the first qubit state is 1. And this C0 cannot be factorized. Like you cannot think of C0 as some unitary operator acting on particle A and some unitary operator acting on particle B. It cannot be factorized. So it is really entangling gate. So maybe C0, Hadamard gate, and some other gates, some pi by 8 gates, maybe Rosenbaum, maybe he can tell that there are some very small number of single qubit gates and C0, you can generate any gate. You can generate any unitary operator. Only you need.
Can you use the mic, please?
C0 operator you cannot decompose into two different Hilbert space. Tensor product or two different Hilbert space.
So there will be some operator which cannot be factorized, but it is acting on the tensor product Hilbert space. It has to act on HA tensor HB. It need not act HA and HB separately. It may act separately, but there will be some unitary operator which you cannot write as U1 tensor.
Then what will be the generic definition? I mean, the construction
Like
of the Hilbert space
operators acting on this tensor product Hilbert space. Some of them will be factorized, some of them will not be factorized.
What is the criteria then? How you can factorize
If
one
you
of
cannot factorize, then it will be of this. So that it can create entanglement in general. If you do what is the physical definition, then I will tell you that it can create entanglement. If you start with the product state, those kind of unitary operator will create entanglement.
I'm just asking, if you take a Hilbert space that is HA, a tensor product HB, that is the Hilbert space, and you have given an operator which act on the total Hilbert space H, let's say, and how you can tell that operator you can decompose or not, looking at the operator. I mean, how you can tell that that operator can be decomposed into two different Hilbert space, A cross B or not? I mean,
sometimes maybe but for the state we will discuss about it. When some density matrix is separable or not. But it is not easy question. Even we cannot decide whether a state is separable or entangled. For the operator also, it will be a difficult problem. Professor Rosenbaum, have you any answer?
And a comment here.
Yeah.
So if it's an unitary operator, I think the Schmidt rank can tell you whether you can factorize it as U1 tensor U. If it has only a single Schmidt rank, then you can actually factorize as U1 tensor U2. But if it has more than one Schmidt rank, then you can't be doing it.
But I have some problem when you are calling Schmidt for it. Anyway, for the timing, if you write C0 you can write, 0, 0, 0, 1, 1, 0, 1, 1, taking these as a basis, it is a 4x4 matrix. Then you can check that you cannot be factorized. But if you ask me, giving a 4x4 matrix, whether it can be factorized or not, there may be some technique, I don't know. But in general, even for density matrix, you cannot tell whether it is separable or entangled. But for 2x2 system, luckily we have some criterion called Perez-Hordecki criterion. Anyway, but how to prepare this ensemble? That was the challenge. Now, so if I start with this state, let this psi is equal to, this is some system C is equal to, say, A0C plus B1C. So the whole state psi C, A, B, it will be, please help me, A0C plus B1C, then coming this entangled state, 1 by root 2, 0, 0 for AB, plus 1, 1 for AB, This is the whole state for these 3 particles. And my aim is to produce this thing on this side. Now, see, can you tell me this is also a basis that you can appreciate, no? This form a basis in for this 2x2 system. So, can you tell me how I can express 0, 0 in terms of this basis? First 2 quantities. So, it will be 1 by root 2, 5 plus 1 by root 2, 5 minus. Similarly, 1, 1 will be 1 by root 2, 5 plus minus 1 by root 2, 5 minus. Because this is a valid basis also. So 0, 0, 0, 1, 1, 0, 1, 1 can be written in terms of linear combination of these 4 vectors. If I do this thing, then I'm writing very quickly that you will see that it will be 5 plus 1/4 Oh, sorry, it is A and C. Overall, there is 1/4. Because what I am doing, I am not doing anything. I am first breaking it. There will be 4 terms. Then I am taking 0, 0 of A and C. I am writing in terms of Bell state. 0, 1 of AC. I am writing in terms of Bell state in AC. In this way, because this is mathematical manipulation. Till now, I have not done anything. Only thing, the state I have written in a different way by changing bases, writing in terms of different bases. So physically, I have not done anything. Now, this is orthogonal basis, so you can perform a measurement in that basis. This is a valid basis. So you can perform measurement in that basis. That measurement can be very easily performed because Hadamard and C naught creates entanglement. So you reverse it. First C naught and then Hadamard. Then this 5 plus will go to 0, 0, 5 minus will be from 0, 1, psi plus will go to 1, 0, and psi minus go to 1, 1. So in a state of making measurement in Bell basis, you can measure in the sigma z basis. But for that, you have to first use the C naught operation between A and C, and then Hadamard. That's why I'm telling, if you have C naught, you can use entanglement, you can measurement in entanglement basis, all things you can do. So C naught is the fundamental thing that you have to implement in our lab. Now you see, if I perform this measurement and I perform the measurement but didn't tell anything to Bob, then if I perform the measurement in this basis, either I collapse here or collapse here or collapse here or collapse here, all probabilities are 1/4. If I collapse here, what is the state of B? Exactly, the state has been teleported from A side to B side. But for the timing, I am not trying to tell that. I am trying to tell whether this ensemble has been produced. You see, this ensemble has been produced because this one can be written as sigma z on psi this is my psi. And this is sigma x acting on psi. And this is sigma y acting on psi. Maybe there may be some global phase factor. So you see that if Alice on these two particles perform the measurement in this Bell basis with 1/4 probability, the exact state will be produced. With 1/4 probability, it will be rotated by sigma z, 1/4 probability sigma x, 1/4 probability sigma y, which is nothing but decomposition of identity with 4 terms. But one thing which Akshan Joshua Wooters did not care about or did not look at, and what is teleportation. See, now if I ask the question, this state is completely unknown to me. It's completely unknown to Alice. And she wants to prepare the state at Bob's lab by some mechanical process. Is it possible without knowing the state? And it is possible actually, because this Bell measurement, this does not involve baby. This does not involve baby. It is a mechanical process performing measurement basis. And not only that, when Alice communicates the result to Alice, so when Alice will collapse on 5+, he will send 2 bits in 0, 0. So Alice will make 2 bits of communication to Bob. If here she collapses, then 0, 0, here she collapses 0, 1, it is 1, 0, it is 1. And earlier they have some agreement that 0, 0 means Alice has collapsed on 5+, 0, 1 means Alice has collapsed on 5-. In this way, they have agreed earlier. Then you see that if 0, 0 comes, these bits come, then Bob will not do anything because he will know that exact state has been performed. If this is the information, then Bob will apply just sigma z as a unitary operator, not measurement. Sigma z is measurement observable as well as unitary operators. So he will apply sigma y as a unitary operator. If this is the result when classical information use 1, 0, he will apply sigma x. When 1, 1, he will apply sigma z, sigma x, which is nothing but sigma y. And exactly the state will be reproduced on Bob's lab. And it is a mechanical process because this identity, what Bob has to apply, either no nothing, or sigma z, or sigma x, or sigma y. So these are fixed unitary operators. So it is a whole mechanical process by which an unknown state will be prepared from one lab to another. So I asked tutors that already you discovered teleportation in your paper without maybe knowing it. But tutors told me that there are some common people in both the papers. Tutors is in this paper as well as teleportation paper. Yeah, this is teleportation, perfect teleportation by using a qubit. By using a how much resources I spend for producing a qubit from one lab to another lab, one maximally entangled state, which I call 1 bit, and 2 bits of communication. So it is interesting that preparing this ensemble does not need any information about psi. Whole protocol does not involve the values of, is totally independent of A and B. That's why it works. But another beautiful thing Sometimes, yeah. I asked my students to see, consider 4 unitary operator, U1, U2, U3, U4, and I give you a 2 particle, A and B, but this unitary operator is acting on 1 particle. But I am giving you 2 qubits. I tell that the unitary operator is acting on one of the particles. It is acting on particle A. So there are 4 possible unitary operators, U1, U2, U3, U4. Give me 4 orthogonal states. So give me an example where you have single unitary operator U1, U2, U3, U4 acting on a single system, and you take a joint system, but unitary operator will act on one of them, and so after this unitary action, you generate a orthogonal state in 4 dimensions. Orthogonal system in 4 dimensions. Now, if I take, let the state of this YA, tensor chi B, sometimes I use tensor sign, sometimes I don't use, it is acting on A. Can you tell me, can I generate these 4 orthogonal vectors in 4-dimensional Hilbert space, I mean 2 qubit system? Or I make the life simpler. Can I choose unitary operators U1, U2, U3, U4 so that acting on this thing on particle A, it will generate the 4 orthogonal vectors? I can choose one of the unitary operator in such a way that it gives me, but second particle I am not doing anything, so it will always remain 0. So this is the highest thing that I can do. I can generate only 2 orthogonal vectors. Because next orthogonal vectors is 1, 0. 0, 0, 1. 0, 1, how will I generate by acting on one particle A? I cannot do it. But again, entanglement can make a magic. We start with a state phi plus, which I have written 1 by root 2, 0, 0 plus 1, 1. Put sigma z on first particle. That means you perform unitary operator sigma z on the first particle. What will you get? Which one you will get? Sigma z is acting on the first particle. How sigma z acts on 0 and 1? Sigma z acting on 0 gives you 0. Sigma x acting on 1 gives you with a 1 with a phase, minus 1. So what will be the state? Phi minus. Sigma x makes 0 to be 1 and 1 to be 0. So which one you are going to get? Phi plus. And obviously, sigma x, sigma z, or sigma y. See, acting on one of the particle, you can generate the full basis. Sometimes when I'm teaching in ISI, I tell C, when it is product state, it cannot generate. When it is entangled, it can generate. So somehow it is influencing the local action on this particle, influencing the particle on the other way. Then they will immediately tell that, okay, then you are telling that some kind of information can be sent immediately. Then I said, no, I didn't mean that. But still I feel that somehow it is influencing the second particle. I try to convince them that, no, I am not telling that instantaneous transfer of signal is possible, but somehow this is happening. And this can be used. This is not a trivial thing. See how. Or sometimes called superconducting coding. So let Alice has to send 2 bits of information. To make life simpler, there are 2 matches. India versus, say, Pakistan, and Indian junior versus Australian junior. And this is knockout match. Either India wins or India lose in both the cases. So if Alice and Bob are told that you can only communicate a 2-level system. You can communicate only 2-level system, like red ball or black ball. Can Alice communicate the result of the matches, both matches? It is knockout matches, of course. Is it possible to send the information by just 1 bit? I mean, a 2-level classical system. So how many 2-level system will be required to send the result of the matches? 2 balls. I mean, if India wins both the matches, then it is red. If India wins first one, but lose the second one, then black. In this way, BR and BB. So this is 0, 0, this is 1, 0, this is 0, 1, this is 1, 1, something like that. So 2 bits communication will be required. But come to the quantum case. Quantum 2-level system can generate infinitely many possible states. So I can encode, instead of taking 2 bits of communication, I can take a single qubit. Because in classical case, if red ball, black ball, that is the end. Or energy level E1, E2, that is the end. But quantum case, you can take these 2, but you can also take so I will, according to the result of the matches, I will tell single qubit. If India wins both the matches, I will send these state. If India wins first one, then I will send one. India wins sometimes. Anyway, India wins the second matches, then I will send this last state. And if India loses both the matches, I will tell the binary state. And Bob will get it, learn the state, and know the matches, because this encoding has been discussed among them earlier.
How will Bob know what measurement will Bob perform to tell the difference between the different states?
And the probability of distinguishing them is 0.
Right.
So though there are infinitely many states for a quantum 2-level system, it does not help. Yes, got it? Because even non-orthogonal, two non-orthogonal states cannot be reliably distinguished. And if it is linearly dependent set, then probability of distinguishing them is 0. So it is of no use. So qubit, though it can generate infinitely many states for encoding, for sending information, it is useless. It is like classical. Only these two states can be used. So in quantum case also, you have to use something like this. I mean, two qubits. So quantum mechanics does not give you any advantage in when communication is needed. But now I ask you a question. Come to the classical world. If I tell you that one ball has to be sent before the commence of the matches, and after the end of the matches, you can send another ball. Now, can you convey the result of the matches? One ball has to be sent earlier, before the start of the match. Now, can you communicate for the exact information? What is coming to your mind? The two balls can be correlated or anything. But what is classical correlation? Red, red, black, black. So, what is coming to your mind? It is possible or not? Someone picks. No, classical world. I am asking about classical. But now entanglement makes a difference. Say, Alice will prepare, before the start of the matches, Alice will prepare in her lab, Alice will prepare the 5+ state. Match has not started. Both the matches have not started. She will send one of the qubit. So they now share 5+. If India wins both the matches, she will apply nothing. If India wins first matches, she will apply sigma z. State will change to 5-. If India wins the second match, she will apply sigma x. The whole state will be psi+. And then if India lose both the matches, then sigma x, sigma z. The state will go to psi-. One qubit has been sent earlier. Now one qubit will be sent. Bob having both the qubits, but they are orthogonal state, they can be distinguished. So Bob will know which particular unitary evolution has been put by Alice, and their encoding has been decided earlier. This makes a big difference. This is dense coding, and not only that, even Alice did not prepare 5+. 5+ can be prepared by Bob. Or even it can be ordered from a company.
Can you use the mic, please?
Maybe it is a stupid question. So 5+ has 2 qubits, right? So if Alice sends one qubit, how can she perform sigma x on that qubit? Like it's like the other qubit on
Other qubit is with Alice.
So she is performing the operation sigma z only on that qubit, right?
Yeah. No, that's why it is interesting that acting on one qubit, you can generate the 4 orthogonal states. That is the property of the entanglement that I just discussed. And I was trying to tell that sometimes I tell my students that when it is in entangled state, by acting on these things, somehow we are influencing the other particle also. But
right, I am asking that acting sigma z on the first qubit, how does it ensure that there is nothing being operated on the second qubit? Because
I'm not telling anything is occurring, but the state is changing from 5+ to 5-.
that is only when sigma z cross identity will act on the state, right?
Yeah, identity means
But Alice has
other part is doing nothing.
Okay, that is understood. Okay.
So I am not very surprised with teleportation, but I am very surprised with this density. Because teleportation is within quantum mechanics. You cannot, teleportation cannot be, what should I tell you? If you forget about quantum information in our classical world, I don't know whether it will happen. But it helps in our classical world. I mean, convey a result of the, convey some real information with just one qubit if it is already entangled with other. It is very, very surprising. And actually, this is so simple mathematics. The paper went to David Marmin. And David Marmin was thinking that how this paper can be published in PRL because it uses so simple things. People already know it. So he was thinking that someday I will reject the paper from PRL. Then he is writing that someday he awoke early in the morning and felt very excited that in terms of information it is miraculous. And immediately write to the editor, immediately publish it.
So the Bob only has measurement on the second bit, or so for distinguishing this for
After having both the particle, you can in principle can perform the measurement in this basis, or what you can do, you apply CNOT, then Hadamard, take them to product state and make the measurement separately. But in principle, you can perform measurement in any orthogonal basis. And you know, because orthogonal states can be reliably distinguished. So you will collapse on one of them.
No, I think what Adib is trying to say is that Bob, in order to find out what state it is, needs to have access to both the.
That's why one qubit is sent earlier.
Yeah, and then once the second qubit is sent, then
After the matches, then Bob will finally have both the qubits. That's why he can distinguish among these four. Yeah. So, tell you one thing. Yes. Yeah. I will just tell one thing which you can work out. Let Alice and Bob share the entangled state phi plus. And this is Alice's lab, this is Bob's lab, this is Charlie's lab. And Alice and Charlie, by two different qubits, they share an entangled state, which is a general entangled state, A00B11, but you can take A00B11, C10 plus D01, like that. But I am telling you, perform the protocol exactly in this way. Like, ignore C. C has to do nothing for the timing. Alice performs Bell measurements, send the information to Bob. Bob acts accordingly. And finally, we'll see that C and B will be in this state. What was shared between Alice, Charlie, and Bob will be, after the teleportation protocol, will be finally shared between Charlie and Bob. The same way I did here, same way, only 4 particles will be involved. What you will do, you will write the full state, then take Alice's particle, both the particle. Alice's 00 you write is as linear combination of phi plus and phi minus. In this way you proceed. You will finally see after the full teleportation protocol, the state that was earlier shared between Charlie and Alice will be finally shared between Charlie and Bob. And Alice will be completely separated from them because Alice will jump to a Bell state after performing the Bell measurement. Yes, I can stop here.
Yes. So what is the advantage of sending it beforehand? You still have to send 2 qubits. So you just send it at the end.
No, but I want to make a difference between quantum and classical. No, Bennett in that paper wrote that maybe after the matches, he didn't write matches. But in my words, I can tell after the matches, this charge of sending a qubit through a channel price will be very high. So you send the 1 qubit earlier when the price is low, something like that. But here I am trying to make a difference in this way. I want to make a difference between classical and quantum. Finally, two-level system is required in classical world. 2 qubits are also required in quantum world. So they are same. But in classical world, if you are forced to send 1 before the start of the matches, then you cannot convey. But in quantum world, because of entanglement, you can do it. So this makes a big difference. As if you are actually sending a qubit after the matches, only the qubit was earlier entangled with a qubit, which is with the same receiver.
No, I understand, but it's still not an advantage, right? You still have to send 2 qubits no matter what. You need 4 orthogonal states no matter what.
Yeah, but this is a big difference that I am trying to tell with classical. And not only that, this 5+ can be 5+, even at least this 5+ can be prepared by Bob, and Bob can send the qubits. Then also it works. But anyway, after the matches, Alice has to send 1 qubits to Bob. But Bob can prepare the 5+ state and send it. And not only that, 5+ can be ordered from a company who will send 1 qubit to Alice and 1 in state 5+.
Alice and Bob have a store of entangled qubits.
Yeah.
That they keep somewhere.
Or they can order a company. Yeah. But having an entangled state in a single lab is not a resource for this kind of thing. One particle has to be in this lab, other particle has to be another lab, and they are entangled. This is a resource in quantum information. Yeah.
So some people, like adding on to what Sir was telling, so some people argue it as saying that you share 1 entangled pair, only 1 qubit. So in principle, you're only sharing 1 qubit because the information is sent through only 1 qubit, and you already have an entangled pair. That's like setup of the lab. That's like understood that you already have an entangled pair. So the argument is, instead of 2 bits, now you have sent only 1 qubit and a shared pair. Like,
yeah, shared pair. Yeah, the language is better. Yeah. But main thing is that by acting on one of them, you can explore the four orthogonal states. This is the beauty, and for product state, you cannot do it.
I have a question. That you were talking about 2 qubits. Is there any possibility of having 3 qubits at the same time? Concurrence of 3 qubits?
With 3 qubits, there may be some protocol, but it can be managed with 2 qubits.
Okay.
But 3 qubits, you can have a more general something, like some information will go to Bob and Charlie. Some kind of things can be managed. But this is, I am trying to tell, maybe there are so many papers involving n qubits, 3 qubits, 4 qubits, 5 qubits, so many quantum information processing. But I am trying to tell on the basic information processing.
Okay.
I don't know much about them, but must be there. Yeah.
And I actually wanted to know how the physics of these qubits will look like in a d-dimensional.
Now, straightforward, if you consider bipartite case, so it is d square kind of advantage.
Okay. Okay.
So with 1 qubit, you can go to 4. With d qubit, you can go to d square number of mutually exclusive information.
So that is called qubit, I suppose.
Yeah.
Okay. Fine. And last question is actually how to measure the entanglement. I mean, in a.
Yet I have not discussed. Maybe
Okay.
in the afternoon.
Okay. 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 Thanks.
Because that involves distillation protocol.
Okay.
That is little bit involved thing, but I will tell the thing.
Okay.
But you know already that you take the marginal density matrix, calculate the von Neumann entropy. Why it is, I will try to tell after.
On? Okay. So, you are saying that, okay, you cannot actually take those two quantum bits and make those four results, four match results, it cannot really get through. So one of those four quantum states were some 0, 1 and 1 and 0 combination, equal combination, right? 1 square root 2, 1 by square root 2. But so my first question is the measurement a single shot measurement?
No, what question you are asking? I'm making, like, are you telling that how can I perform measurement? In this?
No, not that, no, the match thing. So the match thing that you erased on this thing. The match, so India-Pakistan match that you are writing, no? So here you erased. Yeah. Is it the dense coding thing?
Dense coding is something like this. So according to the result of the matches, Alice will apply identity sigma Z, sigma X. There are four
before that, you argued that you cannot do it with a single bit.
Yeah, single.
So there
single
you argue.
Single qubit, you can have 4 states, but it cannot be distinguished.
Right. So that's why I'm asking, is the measurement a single shot measurement? So you measure it only once, or you are sending a stream of bits and you are performing measurement?
Single qubit.
Okay, I see. Okay. So because otherwise, if this was like, if I could send.
Otherwise, if you take two qubits, it's what? No? 0, 0, 0, 1, 1, 0, 1, 1.
No, so not that also. I mean, so let's say I have a way to send this continuous stream of bits, and then I do not prepare my state in a half probability. I can make it a, like, let's say 80-20, 80% 20% probability, or 20-80% probability, right? And then I can measure a lot of things. I mean, I can take a lot of measurements. I can take thousands of measurements, and I can do a histogram, and I'll basically tell what is what. So I can basically send 2 bits, but I have to send it many more times to get the result. Right? But I mean, so okay, so you have to send a lot of bits, but
challenge is whether you can manage with 1 qubit, 2 qubits, something like that.
Okay.
Because you have to send through some channel, and channel is costly.
Okay, I see.